Shh. All right. You've broken into a secret vault somewhere in an undisclosed location in England, and then you get in there and you grab the first thing you can find, put it in a bag, and you get off scot-free. And you're like, all right. And then later you go and open up the briefcase, and you're really lucky because you've got a bunch of printing plates in there, and you're like, yes, I can print all the money, and then that means I can get infinite power, and maybe I can build an Iron Man suit, and I'll be popular, and everybody's gonna love me because that's how money works. And then you look again and you're like, well, wait a minute, these are British 1p coins, and I don't live in England, I live in Canada. So how much money Canadian can I get for printing these things? And also, will the currency exchange accept an infinite amount of British 1p coins? These are all very, very pertinent questions, but then you go ahead and print it anyway, and then you screw everything up because of inflation and the economy dies and everyone's quite sad. Alright, the chain rule. So, when we're working with derivatives of complicated functions, it is useful to have a way of breaking down these functions into simpler elements, and the chain rule allows us to find the derivative of composite functions. So it's very useful. So let's take the example that we just did. So how much money in Canadian dollars can we get for each 1p coin that we mint? Well, there are two conversion factors and functions that we need to consider. The first is that you need to convert 1p coins into British sterling pounds, and of course 1 pound is 100 pence, which means that the function is going to be the number of pounds is going to be equal to 0.01p, if p is the number of 1p coins you print. And then, of course, there is the conversion factor to Canadian dollars. Each British pound is worth 1.82 Canadian dollars, so dollars is going to be equal to 1.82 times the amount of pounds that you have. So to get a function that converts p to Canadian dollars, we need to compose the two functions. So we need to start with the number of 1p coins that we mint. We need to plug it into function 1. That'll give us the number of pounds that this is equivalent to, and then we need to plug it into function 2 to get the amount in dollars Canadian. Alright, so we're going to compose those functions. We're going to get dollars equals 1.82 times 0.01p. So how do we find the derivative using the chain rule? Well, let's look at what the derivative should mean. Well, d dollars over dp, which is the derivative of this function here, should represent the difference or the change in Canadian dollars over the difference in the amount of 1p coins we mint. All right, so how does this relate to the derivatives of the functions that composed it? Well, let's look at the first function in there. That would be the inside function. D pounds over dp is 0.01, and it is representative of the change in amount of pounds over the change in 1p coins that you mint. And the outside function, the derivative of that, d dollars over d pounds, is 1.82, and it represents the change in Canadian dollars over the change in pounds. And you notice how the derivative of this whole thing is actually equal to the two component derivatives multiplied together. And as you can see there, the pounds on top and on the bottom cancel out, and you end up with the correct derivative. And this makes sense because, when we combine two conversions, we multiply the conversion factors. And therefore, this implies that d dollars over dp is equal to d pounds over dp multiplied by d dollars over d pounds. And in this case, we're using pounds as an intermediate variable. We're converting first from 1p coins to pounds, and then we're converting from pounds to dollars. And that is the composition of the two functions. We multiply the two derivatives, 0.01 times 1.82, and we get that the derivative of this whole thing is 0.00182. Awesome. And of course, we can put this in a more general form. dy over dx is equal to dy over du times du over dx. So the u is going to be the intermediate variable that we're using here. But you might be saying like, okay, well, I could have figured this out just by, multiplying the function, and then you can just use the regular derivative rules to get the derivative of the function. Why do I care about the chain rule? Well, we can apply this to way more complicated cases. So what do we do when the composing functions are not actually given? And we'll apply this to a much more complicated function here. So let's say that f at x is equal to x squared plus x minus 9 all cubed. And of course, you can open this up and do your expansion and blah 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 blah. But that's kind of tedious and boring as well. So let's look at how we can do it in a much more simple way. Okay, so let's first of all set all this equal to y, and we'll start. Okay, so first identify the functions that are being composed. In this case, we have x squared plus x minus 9 on the inside, and we have a cubing function on the outside. And what's very important here is that we can actually find the derivatives of both these functions using the rules that we already know, which are the power rule and the sum rule. And then we replace the inside function with an intermediate variable that we choose. In this case, we can put u, I guess. So we'll say that x squared plus x minus 9 is equal to u. Okay, and then of course we'll put that in and we get y equals u to the 3. And now we use the chain rule. We say that dy dx is equal to dy over du times du over dx. So we find the derivative of y with respect to u. Okay, so y is equal to u cubed. Okay, we find the derivative of that. That is going to be 3u squared. We'll multiply the derivative of u with respect to x. U is x squared plus x minus 9. We can get the derivative of that quite easily. The derivative is 2x plus 1. Step 4, the last step, you substitute u back in so that you eliminate that intermediate variable. Now we've got x's on both sides, and that is the correct form. So you simply put x squared plus x minus 9 back in where u was before, and now the derivative is only in terms of x. Yay.